How's it going, everybody? Welcome to this next lecture. In this particular one, we're going to be talking about Kubernetes services and getting into some of the networking aspects of Kubernetes. So it'll get a little bit sophisticated, but don't worry if you've never had any network experience. We'll do I'll do my best to help you out with it as we go along. So let's just jump in and we'll start off with our goals and outline for today. So first off, I'm going to talk about just ports in general a little bit and what ports are, how they work, and everything, because that fundamental foundation will be important to us as we talk about it with containers and networking and all that kind of stuff. But again, we're not going to get super deep into it. Then we'll start talking about Kubernetes services. We'll take a quick sidebar and talk about labeling objects, and then finally we'll finish up with some additional things about services that I just don't get in the first section. So let's start with a ports 101 here, shall we? So how computers talk. Processes listen. Okay, it's not really listening, but they listen using ports on network interfaces. So when a process wants to communicate with another process on a remote machine or receive communication from another machine, it registers with the kernel and says, I want a port. And depending on its privileges and whatnot, where it falls into that port range may vary. A lot of times those are ephemeral ports, which, as it has mentioned here, are in the 49,152 to 65,535. So a very high port range. But again, apps can listen to really any port number. Now, the caveat is only one process can listen to any port at any point in time. And what happens is when the machine on the network interface receives a packet on the network interface, the kernel looks at it and says, okay, who's registered to receive this packet? And it knows that because the packet has the port number on it. And so the kernel takes that payload and puts it into a buffer where then the process can read from the buffer and say, okay, cool, this was a HTTP request, or this is a email notification, or this is a push notification, or whatever it is. So the process is just simply reading from that buffer and then has to interpret the payload and figure out what do I do with this. And the kernel does all that it receives it from the network interface and figures out what process it should go to again. So remember, for any given port number, only one process can listen to it. Okay. Now, where this, as just a super simple example here, we can use a tool called Netcat and run a super simple web server. In this particular case, let me grab the laser pointer here. Boop. All right. While true, do netcat listen to port 8090, and we're reading in this case, a file called response, which this is the file contents. If you don't know anything about the HTTP protocol, no big deal, but when an HTTP server receives a request, it has to send back some HTTP headers and then the actual body. And so in this case, we'd run a very, very simple web server here. Sure, it's not even processing the request, it's just sending a response for everything. And note that for a lot of machines, there's several different network interfaces. There's a loopback interface, which is keeps things on local hosts of 127.0.0.1. But there might also be a Wi-Fi or an Ethernet or a variety of other network interfaces. And a lot of processes, when you say I want to listen to port 8080, for example, they'll listen to it on all of those network interfaces. So just as a fun little adventure here, let's actually run this web server here. So let's jump over to our terminal here. I'm going to do while true, do netcat, and I'm going to list on 8090 and response. Done. Okay. And then I'm going to open up another terminal here, and I'm going to curl localhost 8090, go verbose so we can see the headers. And we see that I got my HTTP response and I got the body here. Now, again, because this isn't a real web server, it's not sending all the requests before it gets the response and all this kind of stuff. Curl may be like, hey, something's not quite right here. But anyways, I can see that I can do curls and I can get the responses that I expect. too. So pretty cool. Again, super simple. I wouldn't use this near anything that's production like. So, all right, let's talk about Kubernetes services now. So we've talked about containers a little bit, and one of the things about containers, best practice, is that really every container should do one thing, but do it well. So most of the time you don't have a single container that does an entire application. So you don't have the web server, the database, the message queues, the caches, everything in one container. That's usually an anti-pattern. So usually what you see is you have one container for the web server, one for the database, one for Redis, one for message queues, one for really any other dependencies that an application might need are split across many containers. And the real reason for that is you're going to have different scaling needs. So if I were running an application that might need to handle thousands of requests, cool. Well, I may scale the front end web server differently than I scale the database. But if they're all bundled in the same container, that makes it really hard to scale one but not the other. And anyways, it's a hard problem. So it's easier to just treat a container, one container does one thing and does it well. Okay. But then the question is, how do we connect the containers? How do they talk to each other? How does the web server know? How do I connect to the database? And how do I know where the database is? How do I find it? How do I connect to it, etc. This diagram here is a pretty popular example app that Docker uses for a lot of their training. And sure, it's a completely over-engineered application, but it's one that we'll play with in the hands-on for this week. So we have a voting app that's written in Python, and it puts any votes that it receives into a Redis cache or pub sub, where then a .NET worker pulls the as votes go into Redis, it takes it and then actually puts it in the database. Okay, and then there's a results app that can query the database and displays the results on a web page. So again, completely over-engineered for a very simple application, but part of the reason they use it is, well, this shows that you can run Python, Redis, .NET, Postgres, and Node all in the same application, just in containers, and it just works. And now, so then the question is, if the voting app needs to go to Redis or the result app needs to go to Postgres, how does it know where to find those different containers? As we saw last week, or when we were working on pod stuff, every application, every container has its own IP address. But those pods aren't guaranteed to have the same IP address if you restart the pod. In fact, most of the time they aren't. So how do we know what IP address we should use for a container? Okay. So for example here, the voting app, these are just numbers I made up here. If the Redis cache is at 10.1.2.192, well, that's cool. How does it know that it's at that IP address? Because that number can change. And in fact, if I were to restart the application or Redis, I may get a different IP address. In this case, it just bumped it up by one, but it could go anywhere. So how do I know what IP address it should use in the first place? But then also, what if it's varying all the time? How do I keep up with that? Okay. And so this was a problem that container orchestration recognized, and they said, well, let's solve that. And that's where services come to the rescue. So services are a network level abstraction that basically sit in front of pods. Services aren't a running thing. Okay, think of services more of just as network configuration that gets applied on every node, and it uses what's called IP tables. And we're not going to get deep into the weeds there, but the idea there is that with services, an application can know that. Right, and we'll talk in a minute how it knows that. But an application can know, okay, Redis can be found at 10.1.0.16, and when packets go to this IP address, kernel rules say, well, actually forward it to this address or forward it to that address. Okay, and so that's what IP tables does, is it sets all those kind of forwarding rules. Now, again, this allows us to now have a static IP address for a service, and then the pods that are behind it can come and go. And yeah, this one should actually say pod 2, so my bad for the slides there. I'll update them soon. But as pod 1 and 2 get recycled, or we add a 3 and 4 or whatever, this service can stay fixed, but just the rules that it uses to forward traffic to underlying pods can be updated over time. Okay. So now the question is, well, don't you still have to know what IP address to use? That cluster IP sure is a fixed IP, but how do we know where to find it? How do we know that that's its IP address? And the answer is DNS. Okay, so DNS, you use it all the time. You may not know it, but when you type in vt.edu in your web browser and press enter, your browser isn't actually connecting to vt.edu. It's doing a lookup and finding out where is vt.edu and goes from there. In fact, maybe let's jump over to a terminal here. If I dig, which is a tool that does DNS queries, vt.edu, it'll tell me that vt.edu, the A record is what resolves the domain name to an IP address. So it says actually it's at 198.82.215.14, which is running in a data center on campus. And in fact, if I curl vt.edu and add the verbose flag, we'll see that it's actually going to connect to that IP address. So DNS is used to translate the domain name into an IP address, and then that's how the networking actually occurs, because you can't talk to just normal domain names. Okay. So DNS resolves domain names to an IP address. Kubernetes runs its own DNS server within your the cluster, and that's what the core DNS pods are that are part of the kube system namespace. And so all services get DNS names, and that makes it a lot easier for us to find services. So now our application, our voting app, can simply say, hey, I want to connect to something that has a DNS name of Redis. And then the DNS server that's running within Kubernetes says, oh, I recognize that name. That resolves to 10.1.0.16. Okay, cool. Now my voting app, the front end, will connect to that. And as it sends packets to that, they're actually going to then be forwarded onto an underlying pod. Okay, so there's some magic going on there. But again, the thing to remember is just that the cluster IP service has a fixed IP address. And then the Kubernetes DNS just makes it easy to find that IP address. Okay, and we'll get some practice with this, so don't worry. Now, one of the things to just note about the Kubernetes DNS names is that there's a lot more going on with them than just saying, okay, I want to look up Redis. Okay? The full DNS for a service is actually a pretty long name. Okay, so there's redis.default.svc.cluster.local. This is actually the full domain name, if you so to speak, the full domain name for a Redis instance that's running in the default namespace. Okay, but one of the nice things about DNS is the DNS resolver that's built into all of the tooling uses what's called a resolve.conf file, and this configuration file configures DNS, and it tells us, okay, what name server are we using? So in this case, it's the core DNS service. But then also these search domains tell the DNS resolver whenever it's trying to connect, here are other names to look up. So what would happen is the first time that the voting app says, hey, resolve the name Redis. Well, Redis actually isn't a valid name, and the DNS service says, I don't know what that is. But since there's a search domain here, what it's going to do is say, well, now try redis.default.svc.cluster.local, and it sends that DNS request. And then the DNS service that's running the cluster says, oh, I recognize that one. Here's a response. And so the search domains are, you can think of them as additional suffixes that as I say, hey, look this up, it'll say, okay, if it fails the initial request, try it now with this other suffix. If that one fails, now try that with this next one, etc. And makes it really easy to find. So theoretically, if I wanted to look at something that's in another namespace, so let's just pretend I have a namespace called test, and I want to connect to the Redis instance in the test namespace, I could do a lookup for redis.test, and yeah, it'll fail the original one because redis.test isn't one. Redis.test.default.service.cluster isn't a real one, but redis.test.svc.cluster.local is a valid name. Okay, so again, I know this may be a little confusing, and once you do the hands-on, hopefully it'll make a little bit more sense how this is all working. So how do we actually make a service? Well, just like in all things in Kubernetes, we just declare an object. So in this case, we declare a service object, and the service object looks like this. we have an API version of V1, a kind of service, and then just like in pods, we have to give it a name. So we have a metadata name, and then we have the specification for the service. Now selectors here are going to be a key value pairs that represent the labels that a pod must have in order for this service to forward traffic to it. Okay, and I'll talk about a little bit more about labels in just a second. But so the pods have to have, in this case, a label named app that has a value of cats, right? And then the rest of this is going to be configuration for the service. So I'm going to expose the service on port 80, but I'm going to send any traffic that comes to the service on port 80 to the target port 5000. And so the target port 5000 is the port number of the pod that in this case has a label of app and a value of cats. Okay. Now, so again, I know this may be a little complicated. Just bear with me here. We'll get through it. We'll actually see it in a second. But before we get too much into services, I want to talk about labeling just really quickly. Okay. So labels are simply key value pairs that can be applied to any object in Kubernetes. Okay. So you can make up whatever key value pairs you want. And they're really used to identify an object. Anything else that can be recorded on it, any other metadata would be used on annotations. And we'll dive a little bit deeper in annotations in a couple weeks, and then it will become clear when you use labels versus annotations. Okay, but labels allow for really efficient queries and watches. So things in the system, for example, services that want to watch pods that have a specific labels on it, well, you use labels here, and it kind of puts them in indexes so that they can be queried and fetched very quickly. And so this is just an arbitrary example here. So I've got some sort of object, it doesn't matter. I give it a name, and then labels key value pairs. Okay, so the labels are part of the metadata for an object. And again, any object in Kubernetes supports labels. Okay, and then I can query using labels as well, especially using the kubectl CLI. Now this is called a selector. So anytime that you're using labels to select specific objects, it's a selector. So in this case, I'm going to do kubectl get pod, and I'm going to use a selector. So I'm going to find all pods that have a app label that has a value of my app, and then another one that has a component label with a value of database. Okay. So in this case, maybe I have all components of my application. Maybe that Docker voting app, I had them all in a single, all the pods have an app label of my app, but then the different components can have different labels based on the component. So it allows me to say, hey, I want to look at all the pods, part of the my app stack, but then it also lets me drill and say, actually, within that stack, I only want this specific component. And so again, selectors let me do that. Okay, so let's go back to services, and we're going to talk a little bit more about the different types and as well what else we can do with them. So there are really three main types of services. And again, services are the way that we expose a pod to the cluster and to everything else around it, and allow other things to connect to it. So the cluster IP type is the default. And this is what allows us to expose a pod internally to the cluster, maybe so that other pods can find it, which is usually the case. Okay? Another example is node port, and I'll do a demo of that here in just a second as well. But node port, what it does is it actually exposes it onto the node and provisions, usually an ephemeral port. You can specify an exact port if you really want to. But then as I access that port on the node, it sends the request to the service, which then sends it to the pod. So there's layers of abstraction going on here. But node port is a really powerful thing, and in fact, we'll talk more about that when we use Ingress here in just a couple weeks as well. Load balancers are really cool, but most of the time we don't get to use them unless you're using a cloud-based environment. But it allows me to say, hey, I want to define a service that's going to be a load balancer, and tooling that's running the cluster will see this and will actually go and provision an application load balancer in AWS, for example. And then we'll configure that load balancer so that as I send requests to that load balancer, it sends it to those pods in the cluster. They're really cool, and it allows a lot of for some really cool automation. And then the fourth one is called external name. I personally haven't used that one too much, but that would be really helpful if you have pods in your cluster that want to connect to something externally, but use just a nicer name within the cluster. So anyways, I won't talk too much about that one. Okay. Now, the final thing to mention, and we'll use these a lot more when we talk about debugging here soon, is that services register their backends where they're going to forward their traffic using what are called endpoint objects. Okay. And endpoint objects really just describe, here's the configuration and here's where I'm going to send the traffic as it comes into me. Okay. And you never have to create them. The Kubernetes management, the services will create them, but it allows you to say kubectl will get endpoints. And so if you expect your service to actually be sending traffic onto something, but there's no endpoints there, then maybe you've got labels mismatched or port mismatch or something's going on there. And again, we'll do some more examples of that here soon. All right, a lot of slides here. I'm sorry. Let's jump in and actually try something out here. So I'm going to go into Visual Studio Code, and we're going to create a pod. We're going to create a service, and we're going to just play around with it a little bit. Okay. All right. So this first pod that I have here is using my little cats demo app. You'll see that I defined resource limits and whatnot. Don't worry too much about those right now. We'll talk about those again in just a little bit. The reason I just have them there is because if I don't, Visual Studio Code complains that, hey, you should have those there, which you should, but anyways, so just ignore those for now. So in this case, I have a pod that has a label named app with value of cats, and it's going to deploy this image, and I'm specifying a container port. Okay, nothing too fancy here. Let's go ahead and apply this. And pod was created. Hooray. All right. So now let's go to my service here. And I see that the service, let me scroll it up just a little bit. So V1 service, it has the same name in this case. I have a selector, and it's going to be using just the same port numbers for each. So I would talk to port 5000 on the service, and that would send it to port 5000 on the container. And that's what the target port is here. Now for kicks, let's mess up the selector, and let's just say not app, just so that it doesn't match. Okay, so my pod has a label of app cats, but I'm going to use a selector that doesn't match, and we'll see what happens here. So let's apply the service, and it says the service is been created. I can do a get services. So you can even type out get services. It can also be abbreviated to, just get SVC. That's just the shorter version of it. And so I see this service named cats here. Okay, that looks cool. But now if I look at the endpoints for cats, it'll tell me that there are no endpoints here. It's saying that, yeah, the service is here, but as requests come to this service IP address, which, let's see, what was it again? So in this case, 10.107.148.157. If requests came to this IP address within the cluster, it says, I don't have anything to forward it onto. Something's not right here. The selectors aren't good. The ports aren't right. Something of that sort. So let's go ahead and fix our selector here. And I'll just reapply it. And now if I look at my endpoints, now it says, hey, I actually do have an endpoint, which is 10.107. And if I look at my pods and go wide, we'll see that matches the IP address of the pod. I know it's doing some word wrapping here. Okay. But now if I go to the service IP address, I'll get cats. Now, one of the things I could do here is let's actually say, this is an app I should be able to access from my machine here. I shouldn't have to do port forwarding or whatnot like we did in our last lecture here. So let's do a node port. Okay, so I'm going to do a node port service here. And now if I apply this, it's going to say, okay, now it's been configured. Let's get the services again. And now what this is going to do is it's going to give me a port mapping here. And this says that port 5000 of the service is being mapped to port 30,665 of my machine. If I open up Chrome here and go to localhost now 30,665, now I'll get the cats app and it's up and running. Okay, So this is really the right way to expose applications. So not through, the way that we were doing it before, with just port forwarding, because that is really just making tunnels and all that kind of stuff. But this is the right way to do it. Now, if I go back to VS Code here, one of the things I can do if I want to specify a specific port. So let's say, let's just say 3555. Okay. And now if I apply this and get the services, now we can see that it picked the specific port that I wanted. Okay. And if I go back to Chrome and go to 3555, come on, there it goes. All right. And it loads my application and I can refresh and see a bunch of dog gifs. Cool. So I can specify ports. Now, the thing about services, though, is I can't use any of the privileged ports, okay? Which, as we saw in the slides, early on with the early on ports, I can't use anything from 0 to 1024. If I want to use any of those privileged ports, I'll have to use the load balancer port, and there's some additional configuration, and we'll talk a little bit more about that when we get into Ingress here soon, okay? So I know there was a lot that we went over. We talked about ports, and again, ports are just listening to, it's more of a mechanism. It's configuration within the kernel to say as requests come in on this port, where does it go? Does it get forwarded on to something else, or does it get put in a buffer that a process can pick it up and listen to? And services let us put this abstraction layer in place so that we can more or less have a fixed IP address and a DNS name resolution for our applications for each of our pods. Now, again, we'll get some practice with it, with the hands-on for this week, where we're actually going to deploy an application that has many pods in it, and they all need to be able to talk to each other. And we'll expose some of them on through a node port, and others we'll just expose within the cluster using just cluster IP so that they can talk to each other. The pods can discover and talk to each other. So again, I know there's a lot here. Bear with me, and we'll get a lot of practice with this over time as we continue on. So as always, if you've got questions, feel free to reach out to me, and we'll go from there. Otherwise, enjoy the hands-on, and I'll see you later. Thanks.